Okay, so I'm recording now. Welcome to your second last class. We're going to take a few minutes here to finish chapter 2. I think there's about 20 slides left or less, and it goes pretty quick. Well, we already did this section last day, and then we'll do some of or most of chapter 3. Chapter 3 is on, so if chapter 2 was all about water, chapter 3 is all about the atmosphere, but it's 30 to 40 slides. It's really short. So last day on Tuesday, we talked about water sampling. If I had all of you, or at least 9 of the 10 of you here yesterday or Tuesday. If you can't remember, or if you missed this, slide 164, these slides here, this is a question on your final exam for sure, like 100%. I don't think I'm going to put this on your last quiz because this question was in lab number 1. Okay, so just make sure you know the 6 steps for water sampling. Again, you can use your notes when you write your exam. You can use, you'll have full access to the internet. So you don't need to memorize this. Just make sure you can find it and understand the 6 steps. All right, so I'm not going to read it again. I'm going to move on to the last part here. Here we go. So guys, section 2.4 is not really a section for the class. This is a section for the lab. It's basically about testing procedures. You don't have to worry about this handout. This is if, we were in a normal semester. I might give you a handout to help you with your lab. This section explains the testing procedures that we would do with the test kits in the lab. We didn't really have labs this year or this semester, not really. We had what I would more call demonstrations. So that's it for section 2.4. We're not going to worry about it. So the last section of chapter 2, and this won't take me too long, is about water pollution. So we're going to learn how, of course, water pollution occurs. Hint, hint. It can be natural, but it's many times, anthropogenic or human caused. We'll talk about different types, and we'll talk about very quickly water pollution prevention methods. So when it comes to your quiz or your final exam, you might want to be familiar with this section, meaning you might want to know the various types, or more specifically, this one at the bottom. I might, wink, wink on your final or on the last quiz, get you to list a prevention method or 2. Again, not really a big deal because you can use your notes. And guys, for the final exam, you'll have a lot of time to do it. So you won't need to rush. You won't be like scrambling, looking for your notes because you think the time is going to run out. Unless you start the final exam D2L quiz like an hour before it closes, you'll have as much time as you need. So just keep that in mind. Keep your notes handy. Excuse me. So water pollution, the definition of water pollution is the contamination of water bodies, of course, and this could be different types of water: lakes, rivers, oceans, aquifers. Aquifers are, I think I'm saying that right, aquifers is probably the right way, aquifers, or groundwater. These can be things we use for fishing, for recreation. They can be protected, protected land where we don't touch them at all. They can be drinking water. So depending on the use of the water, there's different types of acceptable pollution. So the water pollution is what, in fancy terms, we could say environmental degradation, where we degrade or lower the quality of the water. And this could be natural or anthropogenic. And it's when pollutants are put into the water without adequate treatment. And again, this could happen naturally, like a volcano, or the pollution could come from species, natural species. Like, again, I've talked about this a few times, like Giardia. Back home, we call it beaver fever. So this would not be safe for drinking water, but it's not something humans would typically do. So there's different types. We're going to look at them now. So all forms of water are related in a way between the water cycle and the way they kind of mix and join in the environment. But surface water and groundwater, so water above the surface and water under the ground, typically are studied as separate resources and managed as separate resources. So surface pollution, so this is water we see on the surface, could be a lake, a river, or a pond. They generally group the types of pollution into 2 points based on the origin, like where the pollution comes from. And I've talked about these two before, point and non-point source. Point is, again, a type of pollution you can point at the source. It could be a sewage pipe from a plant. It could be, industrial runoff from, say, let's take like an offshore mining facility, in Qatar, where I'm from. They mine, or not mining, sorry, I meant to say offshore oil. That would be a point source pollution, an oil drilling facility offshore. Non-point is, it's not a specific source. It's a group of many, many sources. So this could be, all of the cars in Doha, or I say cars, you know what I mean, vehicles. It could be like on 100 or 200 acres of land, you have lots of different farms for agriculture. That would be, all of that area together would be non-point source. So point source is like a type of pollution that you can point at, just one particular place, and non-point source is kind of spread out over a larger area. So here, there's your definition there, right? It's contaminants that enter a waterway from a single identifiable source. Discharges from sewage treatment, a factory, a city storm drain, like a single city storm drain. All right, it's just one specific point. Non-point is it doesn't originate from a particular source. It's small amounts of contaminants gathered from a large area. So like I said, if you had a large grouping of farms, nutrient runoff from all those farms. That's typically my go-to example. Another one, again, would be like the vehicles. If we're talking about air pollution, and I know we're not yet, but if we were talking about air pollution, the exhaust from all the vehicles in Qatar. If we're talking about water pollution, it could be from all the farming and fertilizer used around Qatar. All right, so there you go. Into the causes. The specific contaminants leading to pollution could be, the range is wide. Obviously, it's typically, we talk about chemical pollutants, things that are, I don't want to say like, not everything's chemical. All matter is chemicals. So it's hard to say it's not a chemical, but typically I don't mean things like sand or just dirt, soil. It's things in that are typically not natural. So it could be, different organic chemicals, fertilizers, could just be pathogens. Some of those are naturally occurring. Some of those could be from biohazard wastes. Water pollution doesn't even need to be a chemical. It can be a physical change too. So it could be it could be temperature based. So that, a lot of industrial plants use water to cool their equipment down. Water is a really good chemical to help with cooling because it has high heat capacity. So if you run water over a system that you want to keep cool, it absorbs the energy, gets warm, you rush the water away. But that water has to go somewhere. So if you dump or, get rid of that water into a water supply, you can elevate the temperature. You could also have discoloration, which would lead to turbidity. Now, again, a lot of discoloration could be chemical based, dyes and things like that. But all of these things together are included in water pollution. So I'm going to kind of go through each of these. Like there's a lot of them. You can see me kind of skipping through my slides. I'm just going to touch on each one really quickly. And guys, wink, wink on a quiz or your final exam, I might get you to just give me one or two causes of water pollution. And you can pick whatever one you want. Again, typically, if this is a normal semester, you'd have to memorize a few of them. But you guys, this is... I want to say you're lucky and I want to say you're not lucky. I miss coming to class and seeing you, and some of you guys might hate this online stuff, but when it comes to the exam, this is good because it's basically open book. So the first one would be anything oxygen depleting. This is obviously a wide range of chemicals. Could be natural, could be anthropogenic. I should say anthropogenic there. Okay, so oxygen depleting, these are things that lower the dissolved oxygen. So it could be an overgrowth of algae, it could be things that cover the water, causes the water to become turbid. So leaves, grass, soil, anything like that. It could be natural, but it could also be man-made or anthropogenic, like fertilizers or pH. We change the pH, the acidity of the water, and it can change the dissolved oxygen. So oxygen depleting substances, any chemical or matter that lowers the dissolved oxygen. Substances that cause turbidity, which blocks the light, also counts. So it doesn't need to be a chemical that changes the pH or something like that. It could just make the water cloudy. So that was oxygen depleting. Up here, it should have said, oxygen depleting. All right. Sorry, you don't need to write that down, but you can if you want to. The next one is definitely not my area of expertise as a chemistry instructor, but your biology teachers would have a really good time with this part, the pathogens. So disease-causing microorganisms. That's certainly a type of pollution we care about as humans. When you look at drinking water, pathogens are something you definitely don't want in your drinking water. And pathogens are, they're not typically seen by we say by the naked eye. What I mean is you can't look at a glass of water and see that it has Giardia in it, for example. That's the example I go to because it's a big problem where I'm from. But you can look at water and see that it's turbid, or you could look at a lake that has no dissolved oxygen and know that because there would be no fish, right? The plants and animals would die off. But pathogens you can't see them. So kind of an interesting type of pollution. A lot of you guys as environmental health and safety might look at this because, again, you can't see this. You'd have to test the water. You test it with, look at it through a microscope or run some tests. So most bacteria in water are natural, harmless. They can be beneficial even, but some obviously can hurt us. So high levels of pathogens can come from, sewage systems, sanitation systems is another word. So septic tanks, a lot of homes, again, where I'm from, have septic tanks. And over time, septic tanks kind of hold the sewage, hold the waste that comes from your house. And over time, they can break down, crack, leak. So these are examples of things that can then leak into natural water systems. Pathogen discharges can be also by poorly managed livestock or farming operations. So think about farms where you would have a lot of animals, hundreds, thousands of chickens and cows. These obviously produce waste, and if it's poorly managed, can leach or leak into a water supply. So these are different types of pathogens I have listed here. Coliform bacteria, not an actual cause of disease, but are used as an indicator of water pollution. other organisms found in water that would cause human health problems. So these might be, I might ask you to list one of these or pick one out of a multiple choice or something. Don't worry about the spelling. I'll probably have these as a multiple choice. But I mean, this is Giardia or Salmonella are ones you've definitely heard about. Norovirus, all of these things I have heard about, or I've known people to get this over time. These are common pathogens that can occur in different surface waters. You just need to list them. You don't need to like define them or talk about what they do to the body. That's for a biology course. These are just some examples of pathogens. Okay, organic chemicals. So again, oxygen depleting, we talked about that briefly. Pathogens, well then there's organic chemicals. So organic chemicals could be detergents, hydrocarbons like oil spills. Okay, that would be a big problem here. I know Qatar is known for natural gas, but anywhere where you are drilling for petroleum products could be an issue, drilling or transporting. Insecticides they use for agriculture to keep the bugs off the plants. Chlorinated solvents. A lot of chemical solvents are used in industrial factories where you make things like polymers, plastics, all of this stuff, volatile organic compounds, again, more solvents. These are all chemicals that should not be, if possible, dumped in any way, shape, or form into a water, any type of water. Like I know a big problem could be detergents. A lot of hospitals, if you think about hospitals, the job that they have to keep things clean and sterile is immense, very large. So think about a hospital, a big one, not a small one, but think about something big like Sidra or not Al Ali, that's big too, but Hamad. Think of all, like literally, think of all the bed sheets and bedding and clothing and everything that they have to wash on a daily basis. Okay, and think about the detergents they use. Now, typically, there are detergents out there that are safe for the environment, but think of 60, 100 years ago, different types of detergents. Some of them are very, very basic. These can really hurt and alter, different water supplies. The water has to go somewhere. It doesn't just disappear. They have to wash it down a drain, and it goes somewhere. So, a lot of things you don't think about, like you think about a hospital, it's a good, clean place, but this detergents can have a really bad impact on water supplies around it. So kind of interesting to think about. There's like not all chemicals are organic. I know there's courses at the college that are just all about organic chemistry, but inorganic chemicals as well. Just remember the difference between the two. Organic are typically carbon-based. They typically you hear they come from living organisms, but the idea is they are carbon-based. Inorganic are things that are not carbon-based. So here are some examples. Acidity, we talked about acidity earlier in this chapter, caused by industrial discharge, so CO2. Ammonia, so ammonia from food processing, fertilizers, different nitrates and phosphates, heavy metals, silt, so sand, different sediment from construction and logging. These are all types of inorganic water pollution. All right, I'm going a little quick. There's not much to really say here. It's just you might have to list a few different types of these pollutions. So I might say, name or list 2 types of organic water pollutants, or inorganic, or in this case, macroscopic. If you've never heard the term, which I kind of doubt that you've never heard this in your biology courses, macroscopic is like the opposite of microscopic. So microscopic, small, we look through a microscope. Macroscopic, large, that we can see without the help of a microscope. This is your common, like when you would talk to a young child about pollution, this is the pollution they would know about. macroscopic is the one you see literally every day in this country and anywhere over the world that you go. You can go out right now and see this, because this would be things like trash, garbage bags, aluminum cans, shipwrecks, things like that. Where I'm from, you see a lot of shipwrecks. They're almost tourist destinations. I know maybe 2-3 hours where I'm from, there's a large rusted ship that people go to see. It's ironically, it's in a national park, but it's a big rusty hunk of metal just sitting in the water for 100 years. And I mean, that's a big form of pollution. That metal shouldn't be there. Nurdles is a word I've never heard before until I started doing this course. These are small plastic pellets. And these can be formed from larger pieces of plastic that break down, become smaller, and kind of turn into pellets over years of moving and bumping into each other in the water. You hear a lot about the plastic problems in health and beauty products, is what I'm trying to say. Like, during this time of the coronavirus, I have a lot of hand sanitizer at my house, and literally next to my coffee mug here, I have a brand of hand sanitizer that I bought from Monoprix a couple months ago. And it's in my hand right now. I guess I could put myself on camera, but in the hand sanitizer, there's little plastic pellets. And I think the idea, it's most of the writings in Arabic, but the idea is these plastic pellets you see in like body wash and hand sanitizer, the idea is they're rough when you wash your body, your hands with them. They're abrasive. They can help clean them. I think that's all garbage. I don't think it's true. But the idea is these pellets help cleaning, or they feel refreshing. I don't know. Either way, they're horrible for the environment. And a lot of countries, I think maybe Canada, maybe the UK, the EU, I don't know, but I know that some countries have banned the use of these microplastics. You might have heard of that before, microplastics. They're typically in health and beauty things. Anyways, it's in my hand sanitizer. I really tried not to buy this, but if you remember, like 2 months ago, everybody was freaking out and there was like no hand sanitizer left in the whole country. I found some at Monoprix and I was like a crazy person. I bought like 3 bottles. Anyways, I still have some. So yeah, microplastics. Try to avoid buying anything with microplastics. Really bad for the environment. Thermal pollution. This is an interesting one because it's like an unseen type of pollution, and it's something you don't really think about. When I think about pollution in the water, I do think about, aluminum cans, styrofoam cups, paper, plastic bags. I guess not paper, but plastic bags for sure. Or sometimes I think of like pathogens, Giardia, salmonella. I think about these things, but I never think about thermal pollution. This is a pollution where the water would have a rise or fall in temperature because of human influence. It's different than chemical pollution because it only changes, it impacts the physical properties of water, which has a chain reaction, right? You change the physical properties, you raise the temperature, you would lower the dissolved oxygen. Right? You raise the temperature, you're lowering the pH. So this has an impact on the chemical properties just by changing the physical property. And I mentioned this maybe 10, 15 minutes ago. A common cause of thermal pollution is using water as a coolant by power plants and industrial manufacturers. They run the water over the hot equipment. The water absorbs the heat and the water gets pumped away, but that hot water has to go somewhere. I mean, an easy solution would be, once you've pumped the hot water away, store it somewhere and let it cool down. But 50, 60 years ago, nobody cared about this. So they would just dump the hot water into a lake or a river, and that's really bad. So again, on your final exam, on your last assignment, which I'll put up today, it'll be a short one because I know you guys probably have a lot of work to do. It's the end of the semester, so it'll only be a couple key questions from the last part of this course. But I might get you to list a couple of causes of water pollution. So you can be specific. You could say Giardia or Salmonella, or you could be less specific and just say pathogens. So up to you. Just know a few of these or have them ready. Okay, guys, we're at the end. I'm so happy. The last part of chapter 2. This course, a little bit better to have you guys in class because at least you can see me and we can be, kind of have discussions and work together. I'm not saying we can't do that online, but it's a little harder. But at least now I think we'll get into a new chapter and you won't have to hear me talk about water for the next class or two. So it might be a little bit more entertaining now in a few minutes when I finish this, because I am today going to start chapter 3. We'll do a little bit of it. All right, so the last part of chapter 2, controlling water pollution. This, guys, this could be a whole course. It's only a couple of slides, but you could do a whole course on methods of controlling water pollution. So decisions on the type and degree of treatment and control, disposal. I mean, there's so many factors on the water supply. What is it used for? What type of water is it? There's so many different types of factors, but the idea is you want to protect the environment, prevent any further contamination. Again, the levels of control, the degree of treatment is completely, situation based. I don't know if I'm saying that right, but are you looking at a lake? Are you looking at a river? Is it in the Middle East? Is it in Canada? What type of pollution is coming into it? What is the water being used for? I mean, is it drinking water? Is it just for recreation? Or is there protected species in there? I mean, so many factors. But some examples of control would be very common all over the world, just simply sewage and wastewater treatment. Some of them are a little bit more, I don't want to say obscure, but ones you don't think about, like erosion and sediment control. So when you're digging and moving around dirt, deforestation could be an example. You might try to protect the soil from erosion, and urban runoff control. So there's storm drains when it rains. There could be ways to filter that out. Typically, a lot of storm drains have little grates, if you know what I mean by that word. Grates. I think I'm spelling this right. Right. So I know they're a little different in Canada, in the Middle East, but I know in Canada, the storm drains have like grates over them. And this is to protect it from, well, I mean, from humans, so kids don't fall in them. Or I don't know if you've seen the movie It, but, so people don't go into the storm drains. But also these things help kind of protect it from macroscopic pollution. So big things like paper bags and plastic cups wouldn't go down in there. That's a very, very simple part of urban runoff control, but just an easy example. In urban areas of developed countries, sewage is typically treated. So most developed countries, any place that has the money would typically have a centralized sewage treatment plant. So all of the sewage kind of goes to one place and then it's treated. And a good treatment plant can remove 90% or more of the pollutant load in that sewage. So, we can do a pretty good job of removing this type of pollution. Some plants, and I don't mean like plants like trees and green plants, I mean treatment plants have even more additional systems to remove nutrients and pathogens. So depending on where you live, the economy there, the type of treatment they have, you can remove 90% or more of the pollution. Industries have different types of treatment because, and again, this depends on the type of industry that it is. Is it a farm? Is it oil and gas? Is it, just polymers or something like that? Different facilities have different types of treatment. Some industrial facilities just have ordinary sewage, right? Like a hospital. Now, a hospital obviously would have biohazard type of pollution. They have a lot of different types of pollution, but a large hospital with thousands of patients, they have just domestic sewage that would be treated by the city's facilities. But other industries can have wastewater in high concentrations, so like oil and grease, heavy metals, volatile organic compounds like solvents, depending on the factory. They can have a lot of different types of pollution, and that means we need specialized treatment systems. So we're not talking about sewage treatment, we're talking about other types to treat specific forms of pollution. So that's, again, not really outlined in this course. We just have to list a few different water pollution control systems, and one of those is wastewater treatment. You don't have to get into too much detail here. Just know that different industries would have to treat their waste in specific ways to that pollution. So the biohazards at Hamad Hospital are treated differently than, say, the oil runoff at Qatar Petroleum. Farms, there's a huge different type of water treatment that can happen at farms, wastewater treatment, because any farm with large amounts of livestock and poultry, so cows and chickens and things, definitely government regulated in developed countries. And, a lot of their waste has to be treated. So animal slurries are usually treated they hold them in anaerobic, so low oxygen lagoons before you dispose them. Constructed wetlands are sometimes used to facilitate the treatment of animal wastes. So instead of dumping animal waste into a natural river or lake or stream, they would be held somewhere else. So a constructed wetland or an anaerobic lagoon, you don't need to know these or anything like that, but just know that the animal waste from a farm in a good farm is not dumped into a natural river, lake, or stream, or the ocean. It is held somewhere and treated there first. Okay, you think of farms as natural and good and they're growing things, but the amount of waste in agriculture or pollution is huge. Between the animal waste, the fertilizers, you even in the next chapter, we're going to talk about atmospheric pollution, the methane and gases, the greenhouse gases alone from the livestock. I mean, it's crazy. So another problem with farming would be the loose soil from when they till the land and they use the land to grow plants. The loose soil washed off fields is the largest form of pollution in the United States, largest source of agricultural or farming pollution, I should say. So farmers may utilize erosion control systems to reduce runoff. So basically, you're trying to prevent the land from running off during heavy rain, things like that. Also, farmers can look at nutrient management systems to reduce excess application of nutrients. There's a little documentary I saw on YouTube about this guy who's growing potatoes, and I can't remember what they called him, but it was really funny. I think it was the Elon Musk. He's the guy who has SpaceX and Tesla. They called him the Elon Musk of potatoes. And he delivers nutrients in this crazy computer controlled regimented method where it's all based on time and weather. So he would look at specific times of the month or times of the year to deliver a very, very precise and minimal amount of fertilizer to maximize its use. So it's kind of he adds the nutrients at the best time. And by doing that, he can use the least amount possible. So it's better for the environment and it's great for his product. Apparently his potatoes are amazing. I don't know if you're a fan of potatoes. But anyways, as technology develops, this is getting better and better and better. The way that farmers can manage the fertilizers and nutrients they apply, even things like genetically modified organisms. I know you hear a lot about that in the news and how they're bad, but a lot of genetically modified organisms I'm going to use the term naturally very loosely, but they naturally fight off pests, different bugs. So we don't need to use as many pesticides. So, I mean, it's an amazing place to work And as you think about the development of technology, how it's changing the way we farm and grow things, this is really interesting. I'm not putting a smiley face there because it's important for your test, but really interesting topic from a science and technology aspect because the advancements are crazy. Very cool. Erosion and sediment control, I kind of just talked about that. It doesn't need to be at a farm or agricultural facility. It could be from deforestation or logging. The idea is you try to prevent the erosion or sediment from moving. So this could be from hydro seeding. This is by growing or trying to grow roots of grass really quickly on the land. When you have things like trees and grass in the land, the roots of those plants hold the land into place. So the reason deforestation can be so bad is the roots of the trees are holding the land into place. This giant network of roots keep the land from eroding. So if you cut down trees, you're loosening the soil to be blown or washed away. You actually see this in Qatar. I remember when I first moved here 6, 7, 8 years ago. I can't remember now, but I remember Qatar. And you're driving from West Bay to Lusail, and you see like this giant hill, and the hill was just covered in dirt. And it was obviously meant to be beautified, landscaped, but it wasn't done. And I remember my mother came to visit and we were talking about it. Like, that dirt back home with the heavy rain, it wouldn't last a month. It would all be washed away. There'd be no hill left. And I remember years and years and years ago, they were trying to put grass on it. And I don't know if you know the term sod. I think I'm spelling that right, SOD. These are like, big pieces of land. Land's not the right word, but like big pieces of soil with grass that's grown into it that you put somewhere, and then that's how you get a garden or a lawn. It's like a ready-made lawn, a ready-made garden with grass. Anyways, they were trying to put the sod there, trying to put the grass there to stick on the hill, and it just never worked for years. Anyways, I think, long story short, they figured it out. Things like hydro seeding. So instead of trying to place a large piece of grass there or a sod, you can seed it with a really kind of like chemically helped seed that grows the grass quick. And when the grass grows, the root system, the grass itself helps control the sediment below it, keeps it from eroding. So a lot of times in farming industries, they'll hydro seed. It's like a liquid spray that just turns into grass. It's really cool. And anyways, growing the grass really quick with this type of chemical hydro seed can help prevent the soil from eroding away. Sediment basins or fences or other ones, you can kind of build ditches so the sediments don't wash away into a lake or river, or you can build a fence to kind of hold the sediment in place. We do this one a lot where I'm from. A lot of times when we build roads and highways, we dig into the ground and earth, and we need to put fences up so that the silt, the ground, the soil doesn't wash over the road when it rains. So anyways, these are just some examples. I think we're getting to the end. Yeah, one more slide left. And the last one is control of urban runoff. So urban runoff would be to slow the velocity and flow of stormwater and reducing the pollutant discharges that come from this. This is an interesting one in Qatar because I don't know how well the urban runoff works sometimes. And you guys probably know that. I'll never forget, years ago, I was moving from Sports Roundabout to a new place. They were closing my apartment building. And so the college, where, obviously where I work, they were going to move my stuff for me because my apartment building was being closed, renovations. So they moved me. The college said they would move all my stuff, but I didn't trust them with my TV. I had a brand new, big, giant Samsung TV. So, long story short, my brother came to pick me up. My brother lived here and he had a big car, a big Land Cruiser thingy, so he could fit my TV in it. Anyways, it just so happened it was in October 2 years ago that it rained in Qatar. And when I say rain, I mean, you know what the rain's like sometimes. It rained like crazy. And to get from Sports Roundabout to Al Gharafa behind the Lulu, the Lulu off the expressway. So Al Gharafa to the Lulu behind it took 5 hours. We had to drive through puddles of water so big it came up to the windows. I mean, it was the craziest day. I'll never forget it. I think we almost killed each other that day, but we talk about it now because it was so funny looking back. But what I'm saying here is the flow or stormwater control here might not be as good as where I'm from, because where I'm from, it rains almost every day. So we're used to it. But here, when it rains, it can really cause problems because it can, completely fill the urban runoff, storm drains and kind of flood the area. But anyways, different types of urban runoff are typically controlled to slow the flow of stormwater, so we're not causing turbidity anywhere, and also to reduce the pollution. Right. So this is the end of chapter 2. It's 1:20. So guys, I'm kind of tired. I know you're probably bored. I'm just going to get a little bit into chapter 3. And that way next day we can hopefully get close to finishing this course. So that's it for chapter 2. Very, very, very large chapter. It's 190 something slides. So I was talking to someone the other day from work, and they couldn't get over how big chapter 2 was compared to the other chapters. Guys, chapter 2 is like 70 to 75% of this course. Maybe even 80% if you kind of include the labs that go with it. So again, this is a little different semester. I was going to say when you're studying, but you don't really need to study. But please, if you can do one thing when you're doing your next quiz or the final exam, try to have your Unit 2 notes ready. And if you can print them or like have them open on like another computer or on your phone or somewhere, like chapter 2, guys, really, really important. 70 to 75% of your final will come from chapter 2, maybe even 80%, 70 to 80% of your final. I haven't made it yet, but I will. Okay, so what is chapter 3, guys? I'll just kind of introduce chapter 3. I'll get a little bit into it. It looks like it's a lot of slides, but they're very quick slides. It's a really interesting and quick chapter. So just give me a little bit more time to do this chapter, or well, like do this introduction to this chapter, and then we can go. All right, so let me share my screen. Sorry, my thing's being weird. Sorry. All right, share screen. Sorry, guys. I've been using this for like 3 months and I still have problems. It's hilarious. All right, just hold up. There we go. All right, finally. Okay, sorry. All right. I like Zoom, but I think there's better things out there. So, Unit 3, second last unit. And I know you guys are thinking, 2 units left. This is insane. There's only one class left. But these units are tiny. This one is actually a lot bigger than chapter 4. We might not get every slide, everything done, and I'm not trying to get everything done. I'm not rushing this at all. I know, we're going not a bit long today, but it might seem like we're going long, but I'm not trying to rush anything. So I'm just going to kind of get us into this, introduce it, and next Tuesday, we'll do as much of this as we can. In the last unit, there's really only one big thing I want to talk about from Unit 4. Unit 4 kind of really links into occupational health and safety, and it talks about like proper labeling and storage. If I can do the labeling and storage part, it'll only take 5-10 minutes. I mean, that'll be great. So we're pretty much to the end of this course. In a normal semester, units 3 and 4 would only take me a class each, but we're dealing with like a class and a little bit left. So it'll be a little shortened, I think, for you guys. But chapter 3, we'll do most of this chapter, if not all of it. It's about air chemistry. And this is a really weird chapter for the lab. You guys are done the labs. There's like the last video about total dissolved solids. That was the last lab. In a normal semester, we would probably have another lab after the total dissolved solids lab on atmospheric chemistry. And you guys are lucky because that's the worst lab ever in this whole college, in my opinion, for me and maybe for you, because it's done outside. Now, think about it. This lab is typically done in the middle of June, every intersession, outside in a parking lot. It's brutal. Now, in the last 2 or 1 year, we've had those little shade covers installed in the parking lot. They were not there 2 or 3 years ago. So we used to have to stand out in the sun for 30 to 40 minutes to collect our samples. It was the worst. The way that the lab worked is we had this device, like I'll call it a vacuum. It sucked the air in, but it had collection vials in it that would collect the air, and then we would test the air for carbon monoxide and nitrogen monoxide and nitrogen dioxide. So it was a really cool lab. The students kept breaking the equipment, so we're only down to like 3 working. Anyways, I won't talk about the lab anymore, but the equipment was iffy. It was not the best, and we had to stay outside in the sun for like 30 minutes. Because you had to collect your sample next to running vehicles, and it was bad. Anyways, you guys don't have to do that. You can stay in your air-conditioned apartments or villas or houses, whatever. All right, so I definitely want to do this section no matter what today, and then we'll check the time. This won't take long, and this might be a little bit refreshing for you because it's not about water. So this chapter is obviously about the atmosphere. So instead of water, we're talking about the air above it. So we're going to look at, and I definitely want to do this today. You definitely want to know some of these outcomes. The first 2 for sure. We're going to look at the composition of the atmosphere. How does water vapor in the atmosphere work? These are not as important, but I will briefly talk about them. But the mixing ratios, if we had more time, or if this was another course even, we might talk about this. The mixing ratios is like mole ratio. So you've already kind of done this in Chemistry 1200 anyways. So anyways, let's get into this so you guys can go. Atmosphere. Now, we have the atmosphere that surrounds Earth. You hear people talk about the atmosphere. You hear about it a lot when people talk about climate change and things, the atmosphere. Well, the atmosphere is not the atmosphere. It's not the only one. Atmospheres surround planets. It doesn't have to be Earth, right? You know, and there's a lot of planets. I'm not going to say how, I don't know how many. The number is crazy, but planets in the universe, in space, have different atmospheres. Some planets' atmospheres are like, excuse me, are poisonous gases, you know, like I can't remember. My best friend, he's obsessed with like space, and he's a physics major, and he'd kill me now, but I can't remember, but some planets are surrounded by methane and things like that. So we're very lucky on our planet. The atmosphere is the gas that it is, which is why we can survive. So just kind of remember that it's not the atmosphere. Earth has an atmosphere. And the atmosphere is a layer of gases surrounding a planet or other material body of sufficient mass that holds it in place by the gravity. So our atmosphere is held in place by the gravity of our planet. It comes from Latin, atmos and sphere, but the idea is it's like the sphere of air that surrounds, in particular, our planet, Earth's atmosphere. Our atmosphere is really special. It helps protect us from genetic damage from the sun. So, you go out and you put on sunscreen, but without our atmosphere, the UVA, UVB rays from the sun, the radiation would, very quickly kill us and other organisms. So the atmosphere protects us from the sun, solar, wind, and other cosmic rays. Our atmosphere also is the product of billions of years of biochemical modification. So it's kind of turned into like this perfect recipe of nitrogen and oxygen and other gases for living organisms to breathe. If you go back and look at the atmosphere, in the time of dinosaurs or before that, it was a little different. So the atmosphere has changed, but right now it's 78% of our atmosphere is nitrogen. 21% is oxygen, and then the third most populous gas, populous, probably not the right word, but third most abundant gas is argon. This you want to know. You don't have to memorize the numbers, exactly, but you should know that if you were going to rank the gases in our atmosphere 1, 2, 3, by far the number one gas is nitrogen. Nitrogen would be like the solvent. So if our gas was a solution, our atmosphere was a solution, it is a solution. It's a mixture of different gases. Nitrogen is the solvent that the other gases are in, and oxygen would be down around 21%. So a lot of people have the misconception that our atmosphere is just oxygen that we breathe with a couple little, contaminants like carbon dioxide and stuff. No. Our atmosphere is by far mostly nitrogen gas. And when I say nitrogen, guys, I mean N2. When I say oxygen, I mean O2. And when I say argon, I mean AR, straight up. Argon is a noble gas, so it's just argon. Carbon dioxide, nitrous oxides, methane, ozone, there's tons of other gases in our atmosphere, but they're 1/10 of 1%. They're very, very, very small amounts. So guys, this graph you definitely want to know, okay? So nitrogen, 78%, oxygen, 21%, argon, 0.9%, carbon dioxide is pretty big, and then, compared to some other gases, and then all the rest. So you don't need to memorize the numbers, but I wink, wink, wink. I might ask you what gas is the most abundant gas, or which chemical, I should say, is the most abundant in our atmosphere. Wink, wink, wink. I always ask that question. It's nitrogen, by far. Okay. Also in our atmosphere is water vapor. And you guys might know more about this if I called it humidity. On humid days, when you go outside and you almost get wet right away, like you feel like you're sweating instantly. That's a day where the water humidity, the water vapor in the air is very high. Some days, which I like them in Qatar when the air is a little drier, it's a little nicer. So under typical atmospheric conditions, water vapor is continually generated and removed in the water cycle. It evaporates from surface waters and then is removed by condensation. So the water evaporates, we get clouds and rain, it comes back to the Earth's surface, it evaporates, it rains, and it goes on and on and on. And it triggers convection currents. These are currents like if you have a convection oven in your house, the heat kind of goes from the top to the bottom and gets cycled around. That's why it heats food quickly and evenly. Well, water vapor being lighter than air, as it goes up and down, it evaporates and condenses, it can create clouds. So very, very important for our weather. Being a component of Earth's hydrosphere and water cycle, hydrologic or water cycle. It's really abundant in the atmosphere, and it can also be a potent greenhouse gas. You don't hear about this a lot. When people talk about greenhouse gases, they talk a lot about carbon dioxide or methane, but water as well. And the reason is water has high heat capacity. So water stores a lot of energy. So if the Earth's climate is rising at, any amount, a lot of the energy can be stored in the air, in the water vapor. And being stored in the air can cause other effects. Just water in general is a heat sink. We talked about that in early chapter 2. The oceans are a large heat sink for climate, as well as the water vapor in the air. So it is a potent type of greenhouse gas that you don't hear a lot about. The percentage of water vapor in the air can vary. It can be almost 0.01%, and up to 4.2% when you have, we'll talk about what the dew point means in a minute, at 30 degrees Celsius. So this is something I'm very familiar with in northern Canada. Sometimes it's so dry in northern Canada, in like, I'll call it like near the Arctic Circle, is, very, very high north Canada. I taught up very, very north on the globe. If you look if you look at Canada and you go really high north, I taught up there. I was a teacher there one of my first years. And in the winter, it would get to -30, -40 degrees Celsius. We had a rule, if it got below 50, -50, which it did, we had to close school. So it's kind of like in Qatar, when it's above 50, sometimes they close things down. Well, where I lived my first year, if it was first year teaching, if it was -50, we would close schools. And the air up there was really, really dry. And it was really interesting to breathe in. It was, I wouldn't say it was bad. It was just interesting. It was so dry. You breathe in and you're like, your nose would almost freeze. It was really, really interesting. So water vapor in very, very cold places can be very, very small. And again, you see this a lot in northern Canada, and I'm sure other places. But you could also get near, like here in the Middle East, near the equator, you can get very, very hot, humid weather as well. I know, like Thailand, I was in Thailand one time in April, and it was in Japan as well in April. It was disgustingly humid. It wasn't that hot out. It was only maybe 30 degrees, which is warm, but it's not 50. But I hated it. You go outside and you instantly are wet from the humidity. So the dew point is good to know when we talk about water vapor. This is the temperature at which dew, which is condensed water, okay, condensed water, guys, it's when it goes from gas to liquid. Okay, so gas to liquid. The dew point is when dew forms, and it's a measure of atmospheric moisture. So sometimes the humidity, the moisture in the air, it's oversaturated, it's saturated, and it needs to condense and come out of the air. This would be the dew point, the point at which the temperature of the air, the gas, the water vapor gas in the air condenses into a liquid. This happens where I'm from a lot in the mornings when the air is warming up. The moisture that's held in that air condenses onto the well, it's kind of not when it's warming up, but it's early in the morning, from the change from the nighttime to the daytime. The gas in the air condenses onto the grass, and we call it dew, D-E-W, and it's when the grass is really, really wet. So again, in the mornings, in the spring or summer, where I'm from, if you go out and lay on the grass, it is soaking wet. And it's from the condensation of the air overnight that turns from a gas to a liquid. It's really interesting. So in the middle of the day when it's really hot, all of that gas has evaporated back into the gas form. But in the mornings when the temperature is just right, it turns into a liquid. It's pretty cool. So it's the temperature to which the air must be cooled for the water to reach saturation, meaning it can hold no more water content. The air can hold no more water. This graph probably explains it better than I am right now. As the temperature goes up, The air, excuse me guys, I just need to take a drink here. I've been talking way too long. I'm going to stop in like 5 minutes, okay? Just give me 5 minutes. As the temperature goes up, the air can hold more water as water vapor. The temperature is higher, the water turns into a gas. So typically at higher temperatures, we have more water in the air. It's more concentrated. So the graph shows the maximum percentage of water vapor that the air can hold at different temperatures. So again, the way this graph works is at negative 20 degrees Celsius, because of the temperature of the air, it can only hold like what's that, 0.1, 0.2% water vapor. It's not warm enough to have the water in the gaseous phase. But as the air warms up, so let's look at 20 degrees Celsius, you can get the air to reach almost 2%, 1.7, 1.8%. Up at 30 degrees, it can be over 3%. The warmer the air, the more water it can hold as a gas. And that's why typically when it's warm, it gets humid. So think about Qatar in December and January in the quote winter, you would never say it was humid. But now in the night times here, as the summer's coming, you go outside, it's a little more humid. And that's because the warm air can hold more water. All right, this is the last thing. And guys, you do not really have, I'm not going to test you on the mixing ratio, but there's one thing I want to get to and then we're done. In atmospheric chemistry, mixing ratio is the mole ratio. It's the amount of one chemical divided by the total amount of all the other chemicals. More specifically, in chemistry, it's the mole of your chemical divided by the moles of all the other chemicals. Now notice I said the other chemicals. We do subtract that chemical from the total. There's no calculations, guys, on your final exam, so you don't have to worry about this formula. This I did want to show you, though. I wouldn't say it's important to memorize. Well, it's definitely not important to memorize, but these would be the, excuse me, I think that's the first time I've sneezed that's going to be recorded on YouTube. Sorry, this is the mixing ratio of the gases in our atmosphere. So we have the big three on top, nitrogen, oxygen, argon. These have a V after them. They're parts per million by volume. So carbon dioxide, compared to all the other gases in the atmosphere, it's 365 parts per million per volume of the other gases in the atmosphere. Neon, much higher, 1800, sorry. Helium, this looks like it's big, but it's, remember, B, parts per billion, 524 parts per billion. So you don't have to memorize this, but these are some of the gases in the atmosphere, and these are basically their mole ratios. So some of these are very, very, very small. Some of them are very, very, very large. The nitrogen is so large, it wouldn't make sense to say parts per million or parts per thousand. We would just say it's 78%. That's it, guys. I think I'm going to stop there. I honestly, I think I should keep going, but I'm not. That's enough for today. So what this means is we might not finish everything in chapter 4 on Tuesday, but I'll make sure I cover the important things that you need to know. One thing I'll mention before you all leave, I had the attendance done. You don't have to worry about that, but the lab. I think I'm going to hit stop record here, but don't leave yet. I just want to mention your lab, guys. So stay with me for 3 minutes, and I'll talk about your lab. So I'm going to hit stop record now. So goodbye to YouTube people, but just stick around, class, for give me 2-3 minutes.